Okay, everybody. Hi, my name is Luca Matteis, and I'm Italian, as he said. So today I'm going to try to explain this new paradigm, which is called behavioral programming. Okay, and okay, you can find me on Twitter, of course. And the subtitle of this talk is "Request, Wait, and Block," and you can see different colors because essentially it's the way that I'm going to describe this paradigm is through these three keywords, which I want you to remember as I explain it to you. Okay. So what is the problem that behavioral programming is trying to address? I would say that the root of the problem is the fact that we have these people on the left, this group of people that are the specifiers, and whenever we build software, whenever we build complex systems, these are the people that interpret the requirements, are the people that create the specifications. And on the right, we have the implementers, and these are the coders. And you can find this sort of dichotomy of people, of these two different groups that are essentially, one group is talking about the behavior and the people on the right are actually implementing the behavior. But if I try to dig deeply about what this problem is, it's, in my opinion, there's a problem of alignments, okay? And what do I mean by alignments? So here I'm trying to explain what the problem is. And on the left, I still have the specifiers, okay? So these are the people that know about what they want the system to do, okay? And on the right, we have the code, and these are, again, coders and specifiers. So here I'm imagining a new requirement, and you can call these stories or even scenarios. And these are things that, if you think about it in a more abstract way, are things that appear in the specifier's brain as they think about them, right? As these little clouds. But the real issue is, in my opinion, is that whenever we convert, so we get these requirements and we convert them into code. Here you can see I'm color coding in blue this scenario, but it's essentially we sort of mix this scenario in the code. So it's sort of spread around different functions. It's described, and we lose touch with it. So as new scenarios come in from the specifiers, we have this problem that it's mixed, right? This idea of mixture. And it's really hard to go back. So from going back from where you can imagine a requirements being, I don't know, when I click the button, I want the model to open and I want the background to become black. Okay, that's the requirements. But how do we implement that requirement? We have to touch lots of different pieces in our code, okay? So here the problem is, again, to stress on, the problem is that there's a problem of misalignments, okay? Between the specifiers and the implementers, we have this problem that they're not aligned. So the solution of behavioral programming is the fact that we can actually make them more aligned. So what if we could find a way that instead of losing touch with the requirements when we code it, we can still keep it this way, and as new requirements come in, we can sort of have this abstraction. And then there can be this magical, here I'm talking about interleaving, but it's very technical, but then there can be this magical interleaving process that sort of puts all our requirements and creates our actual behavior system. So again, here we're on, okay, so this is introducing behavioral programming. It's a paper, and it's very academic at this point, and I'm trying to sort of bring it into the React world, into the UI development world. And it's about maybe from 2012, so it's not extremely old. And okay, essentially, I'm going to try to explain it. But essentially, here this is how it works. It's a system where we program the system using these things called B threads, which are these boxes that appear as these yellow boxes. And essentially, they all run in parallel. That's why they're called threads. Okay. And from a functional perspective, these are function generators, and I'll show you in a second how they work. But essentially, what they can do is they can do three things. They can request for something to happen, so request for an event, that's the blue. They can wait for something to happen, so they can listen out for things that are happening in the real world, and that's the green. But more importantly, in fact, uniquely to behavioral programming, is this idea where we can block, so we can stop things from happening in other threads that are running in parallel. And I'll try to explain how this is going to work. So here I have a function generator. Okay, who knows, by lift a hand, who knows how generators work? Okay, very good. So essentially we can control how this function is executed from whoever calls this function can control its execution, essentially. So here I'm showing a link and a reference, which is a little library that I wrote that is essentially going to execute this function, but it's going to execute it using these request, wait, and block semantics that I just explained. And I'm going to show you how it works. Essentially, when we execute the function using this behavioral system, you can imagine the system that is following the semantics of the wait. Okay, so it's going to actually stop at this section because the current yielded object, it's telling it to wait for a button click, right? And whenever we see button click happening, say on the the UI, so the outside world is triggering this event, it's going to go to the next. So it's going to unlock the execution, okay? And it's going to request increment. And as you can see at the bottom, we have button click and increment. So nothing surprising here. Again, if you're using maybe a Redux Saga, something similar where you can wait for things to happen and then do other things. But here I want to introduce a new thing. I want to introduce a new B thread. And again, alignments with if you can always think about the alignment with the requirements and the alignments with how we're thinking about software. Here I'm introducing a new thread that's called the double click. And right now what's going to happen is because, like I said, they're both executed in parallel, they're both going to wait for the same button click events. And whenever that happens, they will, again, move to the next statements. But here we have this sort of uniqueness of behavioral programming is this block keyword that appears in this new B thread. And this is actually going to not allow increments from being requested from the other thread, okay? And in fact, it's going to block it until we get a button click. I don't know if you can see here the green. I don't have my cursor, but I hope you can see it. So effectively, this is going to run only once we get a new button click, okay? So this is just an introduction about the mechanics of these request, wait, and block, but we can do really interesting things using these three keywords and operators. And I'm going to show you, okay, I'm going to try to walk you through a demo. Tell me if you can see this. Can you see the code? Okay. So here, I'm going to try to explain this. Essentially, we have a board on the right. It's a tic-tac-toe, okay, tris. And right now, the game doesn't do anything. All it does, it's using Redux behind the scene. But you can see a trace of events at the bottom. And as things happen, they're drawn on the board, okay? Nothing surprising. So what are we going to do first? Again, the alignment with the requirements is that we're going to implement a detect wins B thread, okay? You can see the name of the B thread there. It's called detect win by X. It's waiting for an X, but what I want you to really concentrate on, don't get stuck into the details, is that we're waiting for a line, so we're waiting 3 times. That's how the game is supposed to work. And after those 3 things happen, we're going to request or dispatch defect. So you can see how the trace of 3 X's matches the actual B thread, okay? Now, again, this idea of adding new requirements, okay? Now we're going to write a new requirement, and this one is actually very interesting because we're introducing this block syntax, okay? And this new requirement is called enforce player turns. And essentially, the idea here is that the game, I don't know if you understand the idea, but it's not supposed to allow 2 traces of 2 X's in a row because that's not how the game is supposed to be played, right? You should have XO, XO. You should not be able to draw 2 X's in a row. Does that make sense? So to do this, okay. So to do this, I'm actually going to write a new requirement. And here I want to highlight again, we're not changing to implement this new requirement. So I'm not changing how old code was written. I'm just doing things. So here I have an infinite loop, which does exactly what I explained. It's sort of blocking the O until it gets an X. And after that happens, it's doing the opposite. Literally implementing the behavior that I want, okay? So you can see here I'm trying to write an O after an O, and it's not working because currently the system is locked in the block O step, okay? And finally, again, another requirement, which is this idea of disallowing square reuse. So this idea where you cannot draw on top of another cell. But I want to move on before I lose you all with this. With these things, and I want to show you one of the. If you want to, like, if I want your attention for a second about this is the when I was learning about this paradigm, this is what blew me away, and I got into thinking about this the system more. So right now we have all these. Right now we have all these threads, right, that are running in parallel, as I showed you, B threads. So now we want to implement the idea where the computer is going to play with us, okay? And I want you to pay attention to the B thread that we're going to write in a second. So here I'm going to paste a new B thread. And this B thread, all it does, as you can see from, it's called default moves, is that there's an infinite loop, and it's essentially trying to draw O's all over the board, because X and Y's represents all the cells in the board. And when I run this, and if I try drawing X's now with this new B thread, we get this really, really interesting behavior, I'll show you, where the computer is playing with us. So as you can see, as we dispatch X's, there's O's, but why? The question I have is, why aren't the O's being drawn all over the board? The reason they're not is because we have other B threads that we just wrote that are blocking based on whose turns it is, or if the cell was taken already. So this idea of the main feature of this system is this idea where we have essentially positive and negative incrementality. So here you can imagine, as I just showed you, a program made out of these 3 B threads. And as I run them, okay, there's a trace of events, these threads get executed based on the semantics of the request wait and block, and there's a specific trace of events, and that essentially the trace of events is the behavior of our app. Okay. Now, what I can do with this new request wait and block system is that I can change by simply adding a new B thread or a few more, but the idea of incrementality. So by simply adding, I can change the order in which the old ones are executed, okay? So this idea of changing, but this idea is very much, if we think about it, again, it's very abstract, so it's really hard to explain, but this is how we think about things. Like if I'm teaching someone how to play a guitar, I first teach them, okay, whenever you strum a chord, the chord will make a noise, you know, and you can think of this as probably a B thread in your minds. And then as I continue teaching how to play the guitar, like for instance, maybe you have to put your hands in a specific way, and that's a different sound. So all these things they're combined in a similar way to what I just showed you. And here, now just diving back, I hope I'm on time. Yes, I'm good. But here I want to just show you a simple implementation. So since it's a React conference, and this idea can be applied to a variety of different systems, but since it's a React conference, here I'm going to show you a simple to-do list example using Code Sandbox. And so on the right, there's a very simple to-do example with the React component and Redux. And there's a new requirement. Let's imagine the users want a new requirement. Okay, they want to change the system. Specifically, they want something to be deleted. Right now, the deletion doesn't work. Okay, so let's try implementing this using these B threads, using this incrementality. So I'm going to write this function generator, which is called when delete is clicked, delete to do, and very simply, nothing outstanding here. Very similar to Redux Saga actually. Is that we're going to wait for a specific event. In this case, it's the event of the clicking the red button, okay? And then we're going to request, hoping that I forgot to change it, but we're going to request the delete to do, okay? I hope I'm changing maybe I forgot to change the request here. Let's give it a second. Yeah, there we go. So we're waiting for a delete clicked, and then we simply request delete to do, okay? And as you can see on the right, now things are deleted, okay? But let's imagine, again, incrementality. Now, the user comes to us and they're like, okay, we don't really want to delete the item immediately. We want to show maybe a confirmation alert. And after the user clicks on the alert, we want to actually delete the item. So how would we do this? Now I'm going to introduce a little bit of an interesting concept. So I have this component here, which is called delete confirm. And as you see here, this component, it's nothing other than two buttons appearing at the bottom. Okay, can you see those? And this component is a little bit different from normal components because it acts similarly to a B thread. Okay, so it's a generator, but right now it's simply yielding a component. And in fact, all we do is see the two buttons. It's nothing magical. But we can do, thanks to the fact that it's a generator, and also specifically an async generator, we can do something very interesting, and I'll show you now, which is this fact where we can await, or I hope, yeah, so we can await for a specific event to happen, okay? And in fact, now it only appears after the event happens. So we have this interesting way of defining state transitions. And here, if I move ahead, and finally, just this is the end of my demo. It's the last one where essentially the requirement is that whenever the delete is clicked, we don't want to delete it immediately. Okay, we want to wait until the confirmation is clicked. I probably lost all of you, right? Okay, I'm gonna try. Maybe it's gonna be fine, I guess. So here, what I'm doing is I have a new B thread, okay? And sorry, I have a new B thread, and this thread is going to essentially do the same as before. It's going to wait for delete clicked, but this time it's going to block delete to do, okay? Which appears in the first B thread, and this will essentially stop it from being deleted. In fact, I think I even try it. Let's see if I find the code. But we want to block it only until, so we can combine wait and block until the confirm delete event happens. So if I try to comment this out and I do it, we can see that the delete is blocked. In fact, nothing happens. Okay. But now if I uncomment that line, so it unblocks whenever it finds confirm delete, everything works, okay? So here I want to just, before I end, this idea of these scenario-based or B threads, okay? So on the left we have sort of a classic approach, like a state-based approach, where we have the buttons that are clicked and the state changes based on that. And on the right here we have this new interesting approach where we can sort of describe the state transitions very explicitly. So there's actually no state here on the right, but we can still, in a very natural way, understand what's going on, without having to think about the state. So quite interesting. So the question, I mean, this is just to bring it out there. Do we even need a Redux states or React states when we can use generator states? So this is another example using the system where we have an infinite loop. But we're waiting for the specific event, right? Increments, and only increment and then re-render. So it's just a very interesting aspect. But more importantly, this is how the main application of this are reactive systems. This idea of interleaving. If something you go home with, even if you didn't understand, all the complexities of the request, wait, and block, is that these things are very much aligned with how humans think, and the idea that complexity stems from the need to interleave many simultaneous behaviors. But even more than that is this idea where we have maybe a complex system and maybe a system that we don't even want to know. I'm sure many of you have dealt with legacy code, right? And they have to change this legacy code. That's like the most complicated problem in computer science, probably. And if I think that with this system, we can sort of have the idea about the trace of events that we want to make happen in the system, and without even changing the legacy code or the code that was written by dozens of other people, we can implement changes still. So, from an abstract point of view, this is what happens. We have all these threads that run in parallel. They sort of have a specific behavioral outcome, which is the trace of events. But then these green B threads are the things that we change based on the requirements, And this is very much in line with how software is being developed, and it's very different. So quickly, to recap, again, this alignment with the requirements and how humans think about behavior is very important about the behavioral programming. So the ability to add and change behavior without the need to see or understand how code works, extremely important. And again, the nature of software is that it changes constantly. Behavioral programming makes it easier to apply changes incrementally. And finally, state is implicit because of the interleaving that I showed you. We don't really have to like the set state versus the other one. However, of course, there are many cons. I mean, it's a very new paradigm. I'm trying to explain it to you. It's very complicated, but it's, in my opinion, it's radically different, from what we're used to. And ironically, actually, I think that it's even though I think it's more natural, and this is very biased, I'm not saying this is going to solve all your problems. I'm just saying that it's a very interesting paradigm. And does it scale? We still don't know. There's not many people using it, unfortunately. It's brand new, very academic, very theoretical still. And there's, of course, a lack of best practices and tools. So before I end, a couple of acknowledgements. The three main people behind, and these are very serious researchers. David Harrell is the creator of state charts, which is very fashionable nowadays in the React world. And three colleagues of mine who helped me with the slides. So these are some references. And thank you so much for listening to me, and I hope to have inspired you a little bit to think about programming differently.